So in the last video, we introduced the idea that stereochemistry, or a unique arrangement of molecules in space, um, is and can be a very important property. And we want to find a way in which we can describe and characterize and communicate what that specific chirality is. And if we have a chiral center is going to be a atom, typically an sp3 hybridized carbon, that is going to have unique attachments. So it's going to have 4 unique components to it, much like how in our video we had a arbitrary tetrahedral carbon that had 4 unique groups to it. What we're going to use is a set of rules developed by 3 scientists, Cahn, Ingold, and Prelog. That's a lot of words, so we'll often abbreviate it as CIP, first letter of each of their names. And the CIP rules are going to describe how we're going to give a ranking to all of those 4 unique locations, and then use that to determine a handedness, that is a R or S descriptor. Now, we've previously had some amount of rankings. For example, in a Newman projection, we ranked size, and we were trying to put like the big things in an anti-position rather than gauche, for example. The CIP rules, though, are not based truly on size, and that's one of the kind of biggest misconceptions. There's going to be a total of kind of 4 or 3 rules that we're going to walk through, and these are going to describe how we give our rankings. And I want to emphasize that this is not just purely on size. If you see something big like a tert-butyl, that does not automatically mean that it's going to be number 1. So our very first and probably the most important rule is going to be our very first assessment. So you're going to have a carbon, it's going to be tetrahedral, so it's going to have 4 different attachments. We are going to look at the very first atom that is connected to the carbon. So for example, if we had an alcohol, so an alcohol would be an OH, we are going to ignore the H and we are only going to look at the oxygen. Same thing, if you had like a tert-butyl, which would be carbon, 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 we are only going to look at the very first carbon. So for our very first rule, we are going to look at the very first atom that is directly bound to our chiral center. Most of the time it's going to be a carbon as our chiral center. And once we look at whatever that unique atom is, we're going to go through and we're going to rank it by the atomic number. And the atomic number is going to be like what you see on the periodic table. So for example, carbon has a value of 6, nitrogen has a value of 7, oxygen has a value of 8. So if in our kind of like small example where we had like our alcohol and our tert-butyl, the oxygen has a value of 8, where the carbon has a value of 6, so the oxygen wins. Even though there's a bunch of other stuff that tert-butyl is physically bigger, we're not doing just based on size, we're doing based on this specific ranking by our CIP rules. You can also technically have isomers, so like deuterium, which is H2, 2 not as like the subscript 2, but as like superscript 2. That would have like a value of 2. Now, sometimes, for example, like in the original molecule that I kind of showed here, all of these are totally unique and different, so they're all going to have a different atomic number, and then we're good to go. A lot of times in organic molecules, we're going to get some ties. And when we get ties, what we're going to do is we're going to kind of just do rule number 1 again, just on the very next atom. And we're going to kind of just keep going again and again and again until we find a difference. And to kind of show some examples, for all of these different examples, what we're going to do is we're going to assume that over here on our left side is going to be our chiral center. And I'm just going to do a squiggly line for the kind of chiral center. And we're just going to look at attachments off of it. And in each of these, we're going to have a tie in the very first case. So in our very first example, we have a CH3, which would be a methyl group. And in the second one, we have an ethyl group, which is going to be 2 carbons. If I look at each of these, the very first thing that's connected to the squiggle is a carbon. So at that point, we tie. There is no difference. Both of them have carbon. They have the exact same value in terms of atomic number. So we aren't having the ability to give any assessment. So we are then going to then use that atom and look at the three things that are connected to it. And the way in which we're going to write this out is through the bunch of different atoms that are going to be kind of organized. So if I look at the methyl, we're going to have a carbon, and around it, there's a hydrogen, and a hydrogen. And I will often do it where I have brackets to show their attachments and then all the things that are going to be connected to it. You'll see another nomenclature system there where we do like the H's and then a dash. If I look on the right one, the red carbon, I have a carbon, and that carbon is connected to a carbon, a hydrogen, and a hydrogen. So you can write that as a carbon connected to a carbon, a hydrogen, and a hydrogen. Now, when I have things in the brackets, I'm going to put the things that have the highest atomic number on the left and then lowest on the right. So I'm going to put that carbon first and then the hydrogens later. And we'll do more examples in the future where we have multiple different atoms. Here, then, we're just going to do that same kind of ranking. So I see that we have carbon, carbon, they tie. So then I'm going to go to the very next atom. And here I see that I have carbon, hydrogen. That says that this carbon is going to win, and therefore my higher priority is going to be the ethyl. And what we're going to do is we're going to keep going until you find a point of difference. If you never find a point of difference, then there are not 4 unique attachments. So we're done. And it's achiral. Achiral means there is no chirality associated with it. It's not a stereocenter. If we look at this next example, we're going to be comparing a ethyl, so same kind of thing that we saw before, to a isopropyl. And I know it's isopropyl because there's a 3-carbon system and it's branched like a Y, meaning it's connected to a secondary carbon. If I look at each of these, so for example, my blue carbon, I have a carbon, and then connected to it directly is a carbon, a hydrogen, and a hydrogen. The hydrogens here on the that terminal methyl group, we're not going to talk about. We're only looking at that very first carbon. So we're only going to look at like the uncircled stuff of the carbon, hydrogen, hydrogen. On the red carbon, I have a carbon up top, a carbon on the right, and then a hydrogen on the bottom. So I'm going to write carbon, carbon, hydrogen. And again, as we kind of go through our rankings, I see carbon, carbon, that ties, carbon, carbon, that ties, carbon, hydrogen. Now I know that my higher priority is going to be my isopropyl over my ethyl. And that's going to be the kind of general process that we're going to walk through. Now let's go ahead and look at this last one, question number 4. Here we have, if we look at our blue carbon, we have a carbon and it is connected to a nitrogen, a carbon, and a hydrogen. And I'm going to list this nitrogen first because that nitrogen has a higher priority because it has a higher atomic number than carbon. So nitrogen, carbon, hydrogen are going to be my 3 unique attachments on the blue carbon. If I look at my red carbon, I have a chlorine, a hydrogen, and a hydrogen. So I'm going to do the chlorine, hydrogen, and hydrogen. So when I'm doing my comparisons, I see that I do a carbon-carbon, they tie. A chlorine versus a nitrogen is the highest atomic number thing connected to that carbon. Chlorine is going to be bigger than nitrogen based on where it is on the periodic table. So my chlorine wins, and then I'm going to make the ranking for that second group, the red one, being overall higher priority. Everything else we ignore. So for example, if you look at this next comparison, it would be a hydrogen and a carbon, and you would give that down to the blue because carbon is bigger. However, we've already found our point of difference. So all the stuff afterwards, we totally ignore. And that's where it doesn't purely based on size, it actually just is based on our priority. The one final thing that you'll sometimes get is multiple bonds. So what happens if you have a double bond or a triple bond? You'll see these a lot with things like alkenes, alkynes, aldehydes, carboxylic acids, and so on and so forth. And what we do is any multiple bond that we have, it's just going to count as a bunch of single bonds. So if I look at this alkene here, and at the bottom it has a is what we're going to be looking at, where it's kind of connected to the carbon that is part of this alkene has a double bond, and for that double bond, we are going to count that as 2 connections to a carbon. Same thing where you have like a ketone, we're going to count that as 2 connections to an oxygen. A triple bond would count as 3 connections to the same thing. So you're going to really count like how many bonds you have to a specific atom. So let's go ahead and do a quick example to kind of get some practice. So here we have testosterone. And testosterone has a bunch of different chiral centers. And in general, if I'm trying to identify a chiral center, I'm often going to be looking at where I get wedges and dashes. For our sake, we're actually just going to look at these 2 kind of asterisks, carbons. There are other centers that exist on this molecule, but we're just going to focus on those 2. And what we're going to do is we're going to go ahead and just practice ranking each of the different groups that are going to be attached to those yellow highlighted atoms. So if I look at A, which is going to be this top part right here, that is going to be a methyl group. So we have a CH3. So I can write out all of the things that are ranked with it. So I am going to be connected to a carbon, and then my 3 different attachments are going to be a hydrogen, and a hydrogen. If I look over at B, I'm going to have B connected to a carbon up top, a carbon on the right, and then a hydrogen down low. So that's going to be a carbon connected to a carbon, and a hydrogen. And here what I'm doing is I'm just writing that list out that we kind of showed above for our priorities. If I look down at C, C is going to be a carbon, and it has a double bond to a carbon and then a single bond to a carbon. So for the double bond, I have a bond to a carbon, a extra bond to the carbon from the double bond, and then the other carbon, which is off to the right. So overall, I have a total of 3 carbons, which are going to be off of C. And then if I look over at D, that is going to be a carbon. It's connected to a carbon on the left, and then there are 2 hydrogens, which are not drawn in our skeletal structure. So we have a hydrogen and a hydrogen. And those are going to be our kind of rankings that we can write out for our 4 unique attachments. And we see that these are unique because all of these are different. You have different amounts of carbons and hydrogens. So when we do our comparisons or our rankings here, I see my very first one all have a carbon, so we tie. If I look at my second one, I have a hydrogen, carbon, carbon, carbon. This hydrogen is my weakest link, so I'm going to go ahead and give it a ranking of 4. As I then look at the next one, for B, C, and D on the third, I have a carbon, and a hydrogen. So I'm going to eliminate D and give that a ranking of 3. And then finally, between B and C, I have carbon, carbon, carbon versus carbon, carbon, hydrogen. So B is going to be smaller, and B is going to be smaller, and then C is going to be the highest priority. So C has all carbons, where B only has 2, D has 1, and A has no extra carbons. So our ranking here are going to be 1, 2, 3, and 4 in order of C, B, D, and then A. Once we have that, we will go through and give an assessment for handedness, which is going to be right or left-handed, and we're going to practice that in the next video. Let's go ahead and do one more quick practice on thinking about that second atom that we have highlighted and go through its assessments for the 4 unique attachments of E, F, G, and H. E is going to be a lot like A. This is going to be a methyl group, so we're going to have a carbon that is connected to a hydrogen, and a hydrogen. If I look over here at F, F is going to be a carbon. It is going to be connected to an oxygen. There's a hydrogen, which is not drawn, and then a carbon on the other side. So we're going to put those in order. Oxygen comes first, carbon second, hydrogen third. If I look down at G, there's a carbon, and a hydrogen. So G is a carbon, and it's connected to carbon, carbon, hydrogen. And then I look over at H. H is going to be just like what D was. It's a carbon connected to a carbon, and then 2 hydrogens. So in this case, I see all of them are directly a carbon on the very first one, so we tie. So I'm going to look at the second one, which is the first one in the parentheses. I have a hydrogen, an oxygen, and 2 carbons. So right off the bat, I know that the oxygen is going to be my highest priority because oxygen is going to win out. That's going to be the largest in terms of atomic number. And then my hydrogen is going to be last in terms of fourth. I then have a tie between my 2 carbons, so I'm going to look at the next one. And there I have a carbon and then a hydrogen, so I'm going to give my second priority to G and then my third priority to H. So my 1, 2, 3, 4 is going to go fluorine, or sorry, not fluorine, F, G, H, and then E. And this is our CIP rules, going through and then getting an assessment 1, 2, 3, and 4 for the priority of all of our different groups. Once we know those, we're then going to use what we're going to learn in our next video to turn this 1, 2, 3, and 4 into an assessment of either an R or an S. We'll go ahead and stop there, and I will see you in the next one.